Okay, in continuation to the previous lecture, I hope you're enjoying this lecture series. We have discussed what is the significance of complex exponentials or sinusoidal signals. Okay, so two things we have discussed. One is that any periodic signal xt, it can be expressed as a linear combination of complex exponentials only. Okay, which becomes your Fourier series, right? And the second property that we have discussed, that when you pass a periodic signal through a linear time invariant system, the output of the system can be computed again using the help of Fourier series. Okay, because when your input is a complex exponential signal, in that case we have obtained the output which is the same signal multiplied with the frequency response of the system at that frequency. Okay, and based on this concept we analyze how the system basically behaves with different frequencies which are passed through this system. Okay, and filters are also designed based on this concept. Now we will have a look at the discrete time exponentials. We will again take the same thing. In continuous time, there is a property that they are always periodic, but in discrete case, the signals may or may not be periodic. So I take a signal which is periodic with a period of n, and suppose its fundamental frequency is 1 by n. And then we generate again a set of harmonic signals in which all the frequencies are multiple of this single frequency. That is, I generate again a signal class of signals where it is e raised to power j 2 pi f naught kn. Okay, or you can write it as e raised to power j 2 pi f naught is 1 by n into kn. So when you have k is equal to, so k is equal to 0, 1, 2 and so on. Okay, so for k is equal to 1, again as 1n, it has a fundamental frequency of f naught. So as 2n, it has a fundamental frequency of 2f naught. So time period of this is 1 by n, the time period of this will be 1 by 2n and so on. Okay, now there is one difference between the discrete and the your continuous complex exponentials, that if I take s of k plus n of n, okay, this is a class of signals where k can take any integer value. So you have s1t, s2t, s3t and so on. Sk plus n means that this signal is just having at a position of k plus n. It means if you take k is equal to 0, this will be Sn. If you take k is equal to 1, this will be S of n plus 1. So the difference between them is basically n. Okay, so you will get e raised to power j 2 pi f naught. In place of k, it will be k plus capital N into small n. So this will become e raised to power j 2 pi f naught k n multiplied with e raised to power j 2 pi f naught n into n. And in place of this f naught, this is small f naught, sorry. You will write it as e raised power j 2 pi f naught kn into e raised power j 2 pi 1 by n into capital N into small n. So this n and this n will cancel each other. E raised power j 2 pi n. It will simply k is also here along with this. Okay, because k is not there. We have divided this into two exponentials. One is e raised power j 2 pi f naught k into n, then 2 pi f naught n into n. So it will become e raised power j 2 pi n, and this will become 1. This will reduce to 1. So this is again this function, which is nothing but skn. Okay. So what it means is that if you have a periodic signal in the discrete domain, it has only n. It can be represented by n distinct unique frequencies. After this, you will get again the same frequency. Okay, this is what is the meaning. Means S0 has a frequency, suppose S1 has a frequency of f naught, and then when we take S of 1 plus n, it will have a frequency of n plus 1 times f naught. Okay, so those two will exactly be same. Okay, so if you start from any point n naught, so n naught and then n naught plus n minus 1, these two harmonics will exactly be same. If you start from 0 and then you will get n, start from 1 and n plus 1, the difference is n. Okay, so S0 n is same as S capital N of n. Okay, so the signals in the discrete domain will be expressed by n harmonics only. Okay, after that they are same. So if we have a periodic sequence xn in discrete time, it can be represented again in the same form, e raised to power j 2 pi f naught kn, but n limits of n be only from 0 to n minus 1. Okay, this is what is the difference. You are just getting the n samples. Okay, and discrete frequencies, they can completely characterize the signal in the discrete domain, whereas in case of continuous time, you have a summation here from minus to plus infinity. Okay, this is summation for k, sorry, not for n. So you can have c0, you can have c1 up to cn minus 1, and cn will be exactly same as c0. Okay, this is 0 to n minus 1, this will be n only. Okay, so 0 to n minus 1 are distinct, n is in fact same as S0n. This is the one difference between discrete time periodic and your continuous time periodic signals. So when you write the Fourier series of the two signals, in case of continuous time, you can have infinite number of frequencies. But in discrete case, you can represent the signal only by n distinct frequencies. Okay. And the second concept that we have discussed in the previous case, it was when you pass a signal through a system, what we have obtained there is that you pass a signal xt through a linear time invariant system, and you get your yt, which is nothing but the convolution integral of h tau x of t minus tau and d tau. And we have seen that when this is e raised to power j omega t, so yt was simply e raised to power j omega t, or omega naught t to be more specific, single frequency, multiplied with h of omega naught. This is for continuous time case. The same will happen in the discrete case. If we have a discrete sequence xn which is now a periodic sequence, and you pass it again through a linear time invariant discrete system, what will be its output? Okay, output is again the convolution, but in discrete case we have convolution sum instead of convolution integral. So it is h of k x of n minus k. Okay, summation over k. This is how you find the convolution summation between two signals in discrete domain. Again, the operations are same. You fold one signal, then multiply with other, then add. You get one. And fold, shift, multiply, add. There are four operations that you know in convolution. Okay. Now, if the signal is periodic, again it can be represented in terms of complex exponentials only. So if you pass a single frequency is j omega naught n through this system, it will generate a output yn, which is equal to summation of h of k. And in place of x, you have e raised power j omega naught n. So n minus k, it will become e raised power j omega naught n minus k. Okay, so you can write it as summation of hk e raised power j omega naught n multiplied with e raised power minus j omega naught k. Again, since the summation is with respect to k, so this factor is constant. You can take it outside the summation. It will become a raised power j omega naught n multiplied with summation of h of k e raised power minus j omega naught k. Okay, so this is the same concept again. So what you get here is again that your output yn is e raised power j omega naught n into this function. And this function, if you see this is nothing but again the Fourier transform in discrete domain, which is called as dt ft, the discrete time Fourier transform of the impulse response of this system, which has the impulse response hm. Okay, so this is h of omega. So at a particular frequency omega naught, this will become multiplied with h of omega naught. So you have the same fundamental equation here. It means when you pass a purely complex exponential through a discrete time system, the output is the same frequency multiplied with the frequency response at that frequency. So if the frequency response at any frequency is 0, again that signal will be stopped by the system. It will act as a filter. Okay. Now, but there is a difference in the frequency response in continuous and discrete time. So you have two fundamental equations now. For continuous time, when the input is periodic or complex exponential, you have yt is equal to e raised power j omega naught t into h of omega naught. And for discrete case, you have yn is equal to e raised power j omega naught n multiplied with h of omega naught. Okay. Now, as we have already seen that in this case, the frequency range is infinite. In this case, the frequency range is finite. So when you draw the frequency response of this system, the continuous time system, with respect to omega, if you plot the magnitude response, so it can take any frequency and it can take any shape. Suppose this is the frequency response. Okay, it means if you pass this particular frequency, so let's suppose this is 1, this is multiplied with 1, then at this frequency, this is suppose omega 1, omega 2, the suppose magnitude at this is 0.8. So the signal will be attenuated. You pass this frequency omega 2, that frequency will be attenuated by the system. And at any point, if the frequency response is 0, suppose that this frequency omega 3, it is stopped by the system. But this frequency, which is in radians per second, or you can convert this into in terms of f, which is in hertz, it can go from minus infinity to plus infinity, any frequency range. But when you draw the frequency response of discrete time systems, what will be the difference? You have to plot the frequency response only between minus pi and pi. Okay. In fact, it is a symmetric response, so whatever plot we get from 0 to pi, the same will be from minus pi to pi. So we only plot suppose from 0 to pi. So this is the maximum frequency that you can have. Okay. Or we may be from minus pi to pi. Now there is a difference in these frequency variables. This is analog frequency, this is a digital frequency, so there must be mapping between the two. Okay, if you use digital filter, the discrete time system, to process an analog signal, you must know how the frequencies are mapped. Okay, because the maximum frequency in this case, it can be any frequency, it has no limit, but the maximum frequency that you can take here, it should be pi. So how the frequencies are mapped, for that you have to see what should be the sampling time, what should be the exact sampling time, so that you can make sure that the frequencies in the discrete domain should not go beyond pi. It means in discrete time, suppose I have a filter like this, maybe low pass filter, and suppose we have a frequency response like this, omega h of omega. So this is suppose here pi. Okay, and this is a frequency here, maybe pi by 2, at which your gain is suppose 1 by root 2, this cutoff frequency. Okay, this is 1. Now it means all the frequencies beyond this point pi by 2, they are somehow attenuated by the system. Okay, or if you take a more ideal case, you can have a filter like this. This is suppose pi, and this is pi by 2. Okay, so from 0 to pi by 2, all the frequencies are passed. Beyond pi by 2 to pi, these are stopped. This is a low pass filter, this is the pass band, this is the stop band. Now pi by 2 is the frequency if you want to express in terms of hertz. Okay, because anyhow when you discuss about the frequencies, we can understand only the concept of frequency in hertz. Okay, so how you decide that pi by 2 frequency in the digital domain will correspond to which frequency in the analog domain, right? So for that you have to see what is the relation between these frequencies. Suppose I take one example. You suppose design a notch filter for any application. Okay, maybe to remove 50 hertz noise in Ecg signal. Okay, if you use an analog filter, analog system, you have an input signal here, analog signal, which is in this case Ecg plus noise, 50 hertz noise. Okay, and you know that the noise occurs at a frequency of 50 hertz, you have to filter it. So correspondingly, you have to design a system here, a continuous time system, and the frequency response of this system, if you plot in hertz, it must be something like this, isn't it? 50 hertz. So at 50 hertz point, you must have a zero response, zero gain, or you can say null point, so that this frequency is stopped, rest of the frequencies are passed by the system. So it is very easy to understand the concept of frequency response in continuous time systems, or you can also have this axis in omega. So you have to use this relation, simply omega is equal to 2 pi f. So if you normalize this by 2 pi, 50 by 2 pi, that will be the angular frequency omega. Now if I use the same problem, but I use a digital filter for this, It means now my input signal is discrete. This is a discrete time system now. The problem is same. I have an input signal which is signal plus noise, maybe in this case Ecg plus 50 Hz noise. The purpose is to design a filter which is remove this frequency, 50 Hz frequency. So the frequency response will be same. It means at a particular frequency you should have a null point again. Okay, but you can see here is that this frequency response, it can, the maximum you can have go, it can go from 0 to pi. Okay, and how you assure that, and where this frequency will now occur, so that it removes the frequency of 50 Hz in the analog domain. So for that, before you use a discrete time system, you have to convert this analog into a digital signal using the sampling. The sampling rate will decide how this mapping will be happening. Okay, suppose you sample this signal at a rate of fs. Okay, what I do here is that I start a new slide. You have an analog signal xat which is equal to a cos omega t plus phi. Okay, and let us suppose we sample it. We sample at a frequency of fs hertz. Okay, or you can write it as a cos 2 pi ft plus theta. Okay, so you have here some analog signal xt. Now when you sample it, so you are taking the amplitude at discrete intervals. This is how sampling is done. Okay, so you may be taking after an interval of t. So this is 0, you get next sample at t, then at 2t, 3t, 4t, and so on. So t is called sampling time, and if you take inverse of this t, that is called as sampling frequency. So sampling frequency is nothing but 1 by t. Okay, so this becomes, the signal is converted from continuous time to discrete time. Okay, so in order to convert this signal xt into xn, now it becomes xn, what we simply do is that we are taking samples at t, then 2t, then 3t. It means in this equation of xat, which is analog continuous time signal, if I put t is equal to nt, capital T, and n is an integer, we will get its discrete version, the sample signal. So xn, the discrete signal after sampling, is nothing but xa of nt, or we need to know it with xn only. So we put n is equal to 0, you get first sample at 0. You put n is equal to 1, you get second sample at t, then 2t, then 3t, and 4t. This is what is sampling. Okay, and this signal xat, when you sample it, it will become a cos of 2 pi f. In place of t, you will get now nt plus theta. Okay, so this is the continuous signal. Now this becomes your discrete signal after sampling. And if you compare this with the general equation of discrete sinusoid, that is xn is equal to a cos 2 pi fn plus theta. This is general equation. Okay, or you can write it as a cos of omega n plus theta. So if you compare these two equations, what you will get here is that you will see that your f, okay, yes, this small f, 2 pi fn, this is 2 pi fnt. So what is f? This small f in this case is nothing but f into t, by comparing these two equations, okay, and t is 1 by fs, so you can also write this small f as f by fs. So this is the relation between the analog and the digital frequencies. So if you have a frequency f, if you sample it at a frequency of, at a sampling rate of fs, the discrete signal that you'll get, it should have a frequency of f by fs. Or in terms of omega, you can write it as omega is your 2 pi f, so it will become 2 pi f by fs, okay. So this is the relation between the analog and the digital frequencies. So in the analog domain, you have, in the continuous domain, you have omega is equal to 2 pi f, okay. In the discrete domain, you have omega is equal to 2 pi small f. This is continuous time, or you can say analog digital, okay. And your signal was xat is equal to a cos of 2 pi ft plus theta. The signal here is, discrete signal is a cos of 2 pi small fn plus theta. Now after sampling, when you have performed sampling, in this equation you have simply replaced t with and capital T, and this signal was converted into a digital or discrete signal like this, a cos of 2 pi f and t plus theta. So by comparing these two, we have got an equation that is your f is equal to f by fs, or omega is equal to 2 pi f by fs. So this gives you the mapping between the analog and the digital frequencies, okay. It means if I have a signal, suppose as an example you take, a signal has a frequency of 10 hertz, and if you sample it with a sampling frequency of 40 hertz, what will be the frequency of discrete signal? It is nothing but 10 by 40, that you will get 1 by 4, or in terms of omega, this will be 2 pi into 1 by 4, you will get it as pi by 2, okay. Now the question is how you have to decide the sampling frequency for a given signal, okay. And this you can decide from what we have already studied, this relation that you have a infinite frequency range in continuous time, and you have a finite frequency band in discrete time, okay. This is for continuous time signals, this is for discrete time signals. Now when you sample it, you convert a continuous time signal into a discrete time signal using sampling. It means these frequencies are basically mapped. So infinite range of frequencies is mapped into a finite band of frequencies, and you have to make sure that this mapping must be unique, okay. Or when you sample a continuous time signal, The discrete signal that you get after sampling, it must be limited, its frequency must not go beyond pi. Okay, the frequency of this signal, this must not go beyond pi, otherwise you will get aliasing problems. Okay, and how you can assure that? You have an analog signal or a continuous time signal which has some frequency f, a cos 2 pi ft plus theta. When you sample it, you get a discrete time signal which has a frequency that becomes f by fs, or omega, it becomes 2 pi f by fs. So in order for the sampling to be unique, this omega, the maximum value of omega should be pi. It should not go beyond 2 pi. Okay, so for that to happen, your fs, this must be greater than twice of f, isn't it? When fs is equal to 2f, you will get omega is equal to pi, and if it is greater than 2f, this omega will always be less than pi. Okay, so using this, there is a one-to-one mapping between the analog and the digital frequencies, and it will be easy to reconstruct the signal back. Otherwise, if this equation is not followed, what will happen? You will get a problem or a distortion that is called as aliasing. And what is aliasing? In that case, two different signals which are sampled at the same frequencies, they may give you the same discrete time signal. Okay, so this is very important. So whenever you sample a signal, you have to see what is the frequency in the signal first. So you can choose a sampling frequency that should be minimum of twice of the frequency in the signal. You cannot choose less than this. Okay, now in the previous example that we were taking, that if you want to design a notch filter using a discrete time system, so you have a Ecg signal plus 50 Hz noise, and I want a discrete system to filter this noise from the signal so that I get a clean output. Okay, now for discrete time system, obviously this input must be discrete. It means this analog signal, which was Ecg combined with 50 Hz noise, this has to be sampled first. Okay, and for sampling you have to see what should be my sampling rate or sampling frequency. So for that you have to first see what is the bandwidth of Ecg signal. So Ecg signal is generally a low frequency signal in which all the frequencies they are below 100 Hz. Okay, so the recommended frequency sampling or sampling frequency rate for this signal is 200 Hz. So you can choose any rate beyond 200 Hz, but it should not be less than 200 Hz. Okay, now suppose I sample this analog signal at a sampling frequency of maybe suppose 250 Hz. Okay, you had first analog signal which was a combination of two signals, Ecg with a noise, and then we sampled the signal at a frequency of 50 Hz. Now you have to see that where this 50 Hz component will lie in that digital domain so that you can design a notch filter for that. So where f or omega in this case will be nothing but 2 pi into f by fs. This is how the analog and the digital frequencies they will be mapped, f to omega. If f is the frequency in the continuous time, if you sample it at fs, this is the normalized digital frequencies. So 50 Hz frequency will be mapped to f by 250. Okay, or it will be basically 2 pi by 5 now. Okay, it means when you have designed a filter here, a digital filter, which has a frequency response between 0 to pi only, you must have a null point at this frequency, that is 2 pi by 5. So this frequency 2 pi by 5 at omega is equal to 2 pi by 5, I must have a null point. So when you pass this discrete signal through this system, it will remove this frequency from this signal and you will get a clean signal at the output. Okay. So unless and until you have an idea of the sampling frequency, you cannot design a filter. And if you change the sampling frequency, your filter will be changed, the cutoff frequency, isn't it? In place of 500 to 50 Hz, if I had chosen a rate of 500 Hz, in that case my omega will be different, 2 pi into 50 upon 500. So it will become in that case 2 by 5, this is 0, 10 and pi by 5. So in that case I have to design a system like this, which should have a null point at pi by 5, not 2 by 5. Now this filter will pass this frequency 2 by 5 in this case now, because it does not have a 0 here. Okay. So this is how the mapping of the frequencies take place between the discrete domain and the analog domain. So analog domain, this is digital domain. So you have infinite frequency range here, minus infinity to infinity. You have a finite frequency range here, minus pi to pi. Okay. So you have a signal here in the form of a cos omega t or a cos 2 pi ft. When you sample it, it becomes a discrete signal, a cos 2 pi fn. And how the frequencies are mapped, they're mapped using the relation. Your f will become f by fs, or your omega will become 2 pi into f by fs. This is capital F. Okay. So for the sampling to be unique, you must have the sampling rate greater than twice of f. If you assure this, your digital frequency will always be less than pi, or in terms of f, this will be always less than 1 by 2. Okay. So you have to choose the sampling rate in such a way, so either your small f should be less than 1 by 2, or your omega should be less or equal to pi. In that case, there is a one-to-one mapping between the analog and the discrete frequencies. If you choose a sampling rate that is less than 2f, you will get the aliasing problem. And what is that? Let me explain it further. Suppose I take a signal, continuous time signal, with a frequency of 1 Hz. Okay. So you can write like this: xt is equal to maybe cos of 2 pi t, 2 pi f. This is general equation, a cos 2 pi ft plus theta. So if you compare this with this, you see that the frequency of this signal is 1 Hz. Okay. And I take one more continuous signal with maybe a frequency of 5 Hz. Okay. It means it will be cos of 2 pi into 5t, or you can write it as cos of 10 pi t. Okay. This has a frequency of f2 that is equal to 5 Hz. Right. Now let us sample these signals. Suppose we choose a sampling frequency of maybe 4 Hz. for both the signals. If you sample this signal at 4 Hz, what analog signal is or a discrete signal you will get x1, this is suppose x1, this is x2 t. It is nothing but it will be f by fs. Okay, so you will get cos of 2 pi. Now t will be replaced with n and divided by fs, that is 4. Okay, so continuous signal will be converted into discrete signal using this relation a cos 2 pi f by fs, and your t will be replaced with n. This is what I have done. Simply I have divided this with 4, which is the sampling frequency, and replaced t with n. So you get a signal here which is cos of pi by 2n. Okay, now I sample the SAM signal, this signal which has a frequency of 5 Hz at a sampling frequency of 4 Hz. So what I will get here in discrete time x2n, its discrete version, it will be cos of 10 pi n divided by 4. Okay, so this you can write as cos of, it will become 5 pi by 2n. So the frequency of this signal is 5 pi by 2, which is greater than pi. Okay, so obviously when the frequency is beyond pi, you will get a similar signal in a band of minus pi to pi. And you can write this as a cos of, suppose I write it as 2 pi n plus pi by 2n. So become 5 by 2n, and this is same as cos of pi by 2n. Okay, so what it means is that this signal and this signal in discrete time, they are exactly same. Okay, so if you have 1 Hz frequency in continuous time and 5 Hz signal, if you sample both the signal as 4 Hz, you are getting the same discrete time signal. This is what is aliasing. And why it is happening? Because you can see now here we have satisfied this criteria that fs is greater than or equal to 2f. Because the frequency is 1 Hz, the minimum sampling rate should be 2 Hz, but we are taking 4 Hz here. So you are getting the output frequency is pi by 2, which is less than pi. In this case, the signal frequency is 5 Hz. The minimum sampling rate must be 10 Hz for this, but we are taking less than 10 Hz, 4 Hz. So that is why we are getting a aliasing problem. Okay, it means when two different signals, they are sampled at the same sampling rate, the output signal will exactly be same. So you cannot differentiate. If I give you this signal, you cannot differentiate whether this is generated from this or whether this is generated from this. But you can obviously differentiate if you have maintained this sampling criteria, which is called as Nyquist theorem, that if you already chose the sampling rate greater than 2f, this could have never happened. Okay, so you can plot this like this to elaborate more on this. What we have done, we have taken two signals, one with a frequency of 5 Hz and second with a frequency of 1 Hz. When you sample both the signals at a sampling frequency of 4 Hz, the two signals, they become same in discrete time. Okay, so if I plot it, suppose I plot the first 5 Hz frequency, it means in 1 second you have 5 cycles. Okay, so you have 1 cycle, 2, 3, 4 and 5. So this time period is 1 second. So in 1 second you are getting 5 cycles. This is 5 hertz frequency. Now in 1 second you are getting 1 cycle, that is 1 hertz frequency. So 1 hertz frequency we plot. If this is 1 second total time period, so where should be 0.5, or it should be, I think, here. Okay, in between these two, and then somewhere you will get here 0.25 and 0.75. Okay, when you plot 1 hertz frequency, you will get 1 cycle in 1 second. This is 1 second. It means this zero crossing point, it will occur at what time? This is 1, this is 0.5 seconds. At 0.5 you will get the maxima in the negative direction. This should be 0.25 and this is 0.75. Okay, this is 1. It means when you plot 1 hertz frequency, so on the same graph, what it will look like at 0.25, it should be reached at 0. At 0.5 it should go to maximum in negative direction, and this is again zero crossing point, then this, so it should be like this. It may not be exact, but it should be like this. Okay, so this is 1 hertz frequency, this is 5 hertz frequency. Now what is my sampling time? Sampling frequency 4 hertz. It means sampling time is 1 by 4, that is 0.25 seconds. So you take first sample at 0.25 or 0, then 0.25, then 0.5, then 0.75, and so on. Okay, after an interval of 0.25 seconds, this is what is sampling time. So you take first sample at 0, you get this sample. Then when you take the second sample at 0.25, since both outputs are same, it means the second sample should be around here, where the two signals they cross each other. Then at 0.5 you get next sample here. Then similarly at 0.75 it may be here and then here. Okay, it means what it means, the discrete signal that you are obtaining after sampling the two signals, that is same. Okay, whether you sample this signal at 4 hertz or whether you sample this signal at 4 hertz, the output is exactly same. So you cannot differentiate whether this signal is generated from this signal or this signal. This is what is called as aliasing. And how you can remove it? You can simply remove it if you choose the sampling frequency of the signal. If it's greater than twice of the maximum frequency, this situation will never happen, because in that case you will get only one signal which has its digital frequency beyond pi, and that will be unique. You will not get any other counterpart. But if you choose a sampling frequency which is less than twice of f, there is a quite possibility, in fact you are sure that you will get some other signal also. If you sample that signal at the same frequency, you will get the same discrete time signal. So that is why when DSP, before A to D conversion, when you have an analog signal, before you convert it into a digital signal using a to D converter, we use a filter which is called as anti-alias filter. So the purpose of this filter is to remove all the frequencies which are greater than fs by 2. Because fs is greater than 2f, what it means that f is less or equal to fs by 2. It means if you are choosing a sampling rate of fs, the maximum frequency in this signal should be fs by 2. So this is a low pass filter, okay, which rejects all the frequencies which are greater than fs by 2 frequency. So using this you can assure that there will be no aliasing anywhere. Okay, so if you have a sampling frequency of 100 hertz, so the maximum frequency in the signal should be 50 hertz. should not be beyond 50 hertz, otherwise you will get this aliasing problem. Okay, there will be ambiguity in the reconstruction. You cannot, means if these samples are given to you, from this sample you may get this signal also, you may get this signal also, so you cannot decide from which signal actually it was generated, right? So to avoid this situation, we always use this Nyquist criteria. When you choose fs is equal to 2f, this is called as Nyquist rate. Okay, so in general it should be greater than 2f, but even if you choose equal to 2f, that is okay, but you should not be less than 2f. It will create your aliasing problems. Okay, so we may take one more example on this in the next lecture. So this is for today. Thank you.